Using the method of shells, calculate the volume of the solid formed when the region bounded by the lines y equals rad x, y equals 0, and x equals 4 is revolved about the y-axis. Let's try and take a stab at drawing the picture. I've got part of the axis down here, but the square root of x is a curve that looks just about like that and touches here at the point 4, 2. The line x equals 4 is this vertical line. Of course, the x-axis is the x-axis. And this is the region of interest. I think I'll go ahead and straighten that out a little bit. A little better. Good enough. There's your region of interest. In order to create the correct solid of revolution, we'll want to look at the reflection about the y-axis, since we're revolving about the y-axis. Doing this should get us a good sense of what the cross-section looks like. You could tell that this point is going to be -4, 2, if it is indeed the reflection about the y-axis of the point 2, 4. The other side of the solid of interest, or rather its cross-section, we can add in some details, like the circular part of the revolution. And when we do that, we can tell that sort of what we're looking at is this kind of cylinder with a curved cone sort of cut out of it, right? So I'll try and add as much detail as I can to this, but not overly concerned with how it looks. That should be good. We'll leave the white surface as this kind of blank space that we're trying to ignore, because we are interested in the solid, the blue part basically, the blue part of the solid. And we're instructed to use the method of shells to calculate the volume of that solid. In order to do that, we're going to have to get a sense for what an arbitrary shell might look like. Well, if we sort of take two strips out and revolve them around as such, this is usually the part where my artistic skills break down, but giving it the best shot I can. What I have attempted to draw here is a little shell that is bounded below by the x-axis and bounded above by the line y equals the square root of x. So I guess I would have a wall like that. And we're going to think about this solid as being a collection of shells stacked on top of each other. So it might be helpful to think about the volume of a singular shell. This shell, you might notice, is basically a circumference of a circle with some thickness and height. So if you think about this as being the circumference of a circle, 2 pi times its radius, with some thickness, t, multiplied by some height here, you'll have a good place to start as far as solving this problem goes. But we'll have to get more specific than that, and we'll want to think about what makes up each of these components, the radius, the thickness, and the height. Well, the thickness seems to be a small distance measured along the x-axis. We will call it delta x. The height appears to be given by the difference between the x-axis and the line y equals the square root of x. And the radius is given by a point along the x-axis. Make a little bit of room for that. A point along the x-axis for the radius. So we could talk about the volume of our shell that we've drawn as being 2 pi x square root of x for the height, and then the thickness, which is delta x. One simplification or 2 maybe. We could think of the x as square root of x as x to the 1/2 power. And we can combine those two x terms and get x to the first times x to the 1/2, which by rules of exponents will be adding 1 and 1/2, so you'll get x to the 3/2 delta x. And it would perhaps be reasonable to say that the volume of all my shells, plural, is a summation of some kind, a summation of 2 pi x to the 3/2 power delta x's. And we would want to sum up our shells from where x is equal to 0 all the way to where x is equal to 4. As we've defined each of the variables, that would give the correct numbers for the height and the radius for every shell that we're going to have. And so, using calculus methods to think about this summation, we talk about an integral from 0 to 4 of 2 pi x to the 3/2 power dx. Doesn't appear to be a difficult one. I'll call it 2 pi. Performing the integral, we will have x to the 5/2 power divided by the new exponent of 5/2 evaluated from 0 to 4. Or rather, 2 pi 2/5 x to the 5/2 power evaluated from 0 to 4. Or still rather, 4 pi over 5 x to the 5/2 evaluated from 0 to 4. Which my calculator tells me 80.42.